ready to go?
Yes.
Okay, so we have another talk on software engineering modeling now, on recommenders rather than meta modeling. I'm sure you can introduce yourself better than I can, so off you go. Thanks.
Okay, good afternoon. My name is Lissette, and I'm going to be presenting reuse and automated integration of recommenders for modeling languages. This work is done together with Antonio Garmendia, Esther, Guerra, and Juan de Lara from the Universidad Autónoma de Madrid. So here's an agenda of what I'll be talking today. First, I'm going to introduce recommender system and a little bit of the context where we're going to use it, the current situation we have, some challenges, the proposed approach, architecture and tool, and a conclusion in future work. So recommender system are software tools and techniques that suggest items that are relevant for a particular user. And as we know, these recommender systems today are available in Netflix, recommendation movies, and other sites for music like Spotify and so on. So in the context of model-driven engineering, here we have a class diagram. On this part here, the class diagram have a class professor, and here professor have two attributes, pretty simple, and in this particular moment of the developing of this model, the modeling engineer wonder what other attributes maybe want to add to this class. So from a data set of models that's conveniently stored somewhere else, so an algorithm use this information. I am so sorry. This algorithm use this information and suggest, wow, I'm sorry, and suggest, here suggests to add surname and birthday, considering that maybe this class is similar to the class saved in the dataset of models. So basically, that's how it works, recommender system in model-driven engineering. And in this example here, to add extra information, the target could be university, in this case, a class, and an item could be the attributes. Also, it can be interfaces, for example, and the interaction between these target and item is what create an interaction with will be given the positivity that this target need or use in the past this particular attribute. So the current situation is that we have many recommender systems for modeling tasks. Here are some papers previously published where you can have recommender system for meta modeling and a core recommender system for UML using different algorithms like context collaborative filtering of NLP. So this recommender system, as I mentioned, they go for a variety of different recommendation methods. They are targeted to concrete languages, and normally they are developed for independent tools, and even sometimes they just get to the point where you do offline evaluations, but never is integrated to any modeling tool. So from this current situation, we have the need to integrate these recommenders that are not being used in action, or normally this type of integration take a high development effort. And currently, you cannot reuse a recommender system that is developed, for example, for a core to use it on UML-based modeling tool. So the big question is, can we reuse this recommender system for my modeling notation, and can I integrate them in my modeling tool? So we have here 4 different challenges for this. The first one is the target modeling language. As I mentioned before, we have some of them being developed for core, for UML, for other modeling languages. So ideally, we would like to know if we can reuse this in different notations. Second, the recommendation sources, they're coming from different places. Some of them are deployed in an API. Some of them are, you have to download and install it yourself. Number 3 is the recommended items. Sometimes they recommend, as I mentioned before, attribute for classes, but they can recommend packages to other projects and so on. And finally, the modeling environment. Some of them are deployed, some of them are not deployed, or some of them are deployed for a specific modeling environment. So before I go to the proposed approach, I'm gonna depict this dimension that we did to explore how we can do this reuse and integration. So first we have the target modeling language. As I mentioned before, it can be homogeneous if it's for the same modeling language that we're gonna use it in the same one we develop it, or if you're gonna use for a different one, which is gonna be heterogeneous. The recommendation sources can be local, if it's just directly in your Eclipse or your framework, or remote if you can access through a remote service. The recommendation items, it can be for multiple targets. You can have different targets at the same time, different domains. Sometimes these recommender systems for model engineering that are domain specific are developed for only bank domain recommender system and so on. So you maybe have multiple domains. And finally, the aggregation rank. If you have the same type of item being recommended for a particular target, you may need to rearrange all those recommendations if you aggregate multiple recommender systems. So for this one, you have supervised and unsupervised, and unsupervised have majoritarian and positional. And finally, the modeling environment. Here, which is the detail you're going to use it. It can be graphical, textual, or tree-based, or the interaction, if the recommendations are going to be reacted, if you have to ask every time you want a recommendation, or proactive if the recommender system can know where in the active model you are, so it can recommend something appropriate. So our proposed approach is a Eclipse plugin called IronMan, which means integrating recommenders for modeling languages. It's for the reuse and integration of recommenders into existing modeling tool. And IronMan guides you on the discovery and selection of recommender system, adapting to different notation if it's needed, configuration of these aggregation methods for how you're going to re-rank the recommendations, and finally the deployment on, for the moment, Sirius and tree-based modeling tools. So here we mark the ones that we currently support in IronMan. So first, for the overview of the methodology, this work is supported in our recommendation service API. Here we have two. The recommendation service indexed is the one where we're going to register all the different services, and the recommendation services is the one that these registered services have to comply to the endpoints designed there in order to work with our methodology. So first, in IronMan, you have to select the recommenders available. All the recommenders or recommendation services that you had indexed previously are going to show here. You're going to select the one you need. Then you're going to select which targets and items you want to use. Afterwards, you have to adapt it to the modeling languages if the notation is different from the one that was conceived for. Then you select the aggregation method if, as I mentioned before, you have similar item types for a particular target. And then you configure the modeling tool or the detail you want to deploy this recommender on. And then you go for deployment. And finally, you have these integrated recommenders on the modeling tool. So just for a quick view of how these endpoints work, it's very simple. The recommendation indexer basically have two endpoints for register and update this registration. And the services in Discover is the one who allowed IronMan to access to all these recommender already indexed in order to connect it to the Eclipse. And the recommendation survey API, which is the one who the recommender have to comply with. You have two endpoints. One is called features that have to contain all the metadata that we need. So for example, in this case, we have here in the A section, this is a class diagram as we saw before, and this is how it's going to be encoded for JSON for our tool. So here, for example, in this case, the E class is the target. Here we have the target features. We have to specify which is the right property, because a lot of these tools or tree-based tools and Sirius-based tools, you collect information from one place, but then you need another way to access to write this information. So we make a difference between which is the written property, this will be the read property, and which one will be the item, and which is the item feature. So all this information here is encoded in this base. So all the recommender systems or recommender services that you want to index have to follow these particular endpoint. And the second endpoint is the one for the recommendation. So here you have recommend with a name, and then this is some query parameters that you can use. So basically here, for example, you have a current scenario, an active model that you're working on, similar to the one we saw at the beginning. And this is the encoding that you need to provide for requesting a recommendation. So using these two endpoints, then the rest of the work is done by IronMan. So for the adaptation, there is more detail in the paper, but if you see here, we have a pretty simple adaptation for the different annotations. Currently, we are working with notations that are quite similar between the target and the source of the recommender, but we want to work in the future with more complex ones. Here, if you see, we are mapping, for example, an E-class is equal to a class, and then name to name. Here, a structural feature in the write property is on attributes. All attributes in the read property is all attributes. E attributes correspond to property and name to name. So it's a structure per server mapping. This is quite simple, as I mentioned before. So, but the idea is that we are mapping where each one of these recommendations from the one that was designed for is going to go to. And for the aggregation method, also we have 3 different aggregation methods. This example here is for one that's called board account, which is quite simple. Also, here, for example, we have, imagine you have 3 recommender systems from the different notations that are recommending you different things for a particular class, for example. So these 3, you calculate different scores based on their positions and if they repeat between themselves. And finally, here you have a summary of all these scores. And depending on the tool you're using, you may want only the top 5, top 10 recommendations, then this will be returned. So for the architecture and tool support, as I mentioned before, here IronMan will be communicating directly to the recommended service indexer through these 2 endpoints, which is the one who allowed to see and discover which recommendation service had been deployed. We also or have to work from the support of the meta model of the recommender and the meta model of the DSL. So all this work is done for Eclipse. So you need to have install, all this meta models support in order to have it available in IronMan in order to do the mapping, for example. So here we have 2 extension points. One for the aggregation method. As I mentioned before, we have board account. Also, we had our ranking and media rank aggregation. Here, also, we want to explore in the future with more aggregation methods. And also, we have another extension point for the modeling tool or the editor we're going to use. Here, we have support currently for tree-based and Sirius editor. So here, through, in the case of Sirius, both of them actually go directly request of the recommend through the recommendation services API. And in the case of editor, they go to the recommendation system layer, which is a layer provided by Sirius, where we inject these recommendations. And in the case of the tree-based editors, we directly inject it in the menu. And in these cases, all of these integrations are done without source code or anything. It's just using the layers of the menu available in the different tools. So I'm going to make a simple example of how to use the IronMan. And in this case, we're going to showcase a little bit of how to integrate 2 different recommender systems for 2 different notations and different tools. So the first one, we have the recommendation system selection. So here we have 2 recommendation services already indexed. After we index it, all this information is collected through the features endpoint that have all the metadata. And here we select which recommender systems we want to use for this case. Second is the item selection. So here, after we select the recommender system, we see here the recommender system we selected and which are the items are available. In this case, all of them have available attributes and operations. The third one is adapting the recommender system. As we saw before, some of them are in the core and some of them are in UML. So the ones who are in UML, we want to adapt them to a core because we're going to use them, all of them, in a core-based recommenders. So here, for example, as I mentioned before, it's simple. You can look here in add modeling language. You look through there that you have installed the meta model of the UML in this case, and then you're going to select which one is the one who's going to adapt to. So that way it's going to be automatically integrated there instead of the original where it was deployed. The fourth one is aggregation of recommendations. Here you just choose which algorithm you want to use for this aggregation. Then is environment selection. Here you have to choose from the environment available which one you want to use to deploy this. Here we select both of them, Sirius and Tree Editor. In the cases of the tree editor, you don't have to do anything. It's only have this menu layer available, and it's going to go directly to where you have to go. But in the case of Sirius, we have to choose the diagonal representation and do another selection for this particular aggregation. And finally, deployment. So here is how it will be deployed. We have a couple of images. For here, this is the integration in a core tree editor. So here you can see a regular core tree editor, and when you select the recommendation, you can see where it's coming from, what is the rating to have. This rating is coming after the aggregation, because if not, it will have the score from the original recommender system, and which are the recommendations that you have. In this case, this is a Sirius editor, it's a specifically obey UML designer. So here you can see also where the recommendations are coming from and which type of recommendation. You select what you want, and it's going to be added automatically to the class diagram. So for the evaluation, first we want to see if we can adapt this recommended system to different languages, and if we can integrate it into third-party modeling tools or existing modeling tools. So for the evaluation, we use two recommender systems, one for core meta models and one for UML class diagrams. We use it for 4, meaning other 3 different languages, each one of them to use one of these ones. And also, we integrate it in different modeling tools. So here, this is the experiment results. First, here we have how many integrations we did, the recommender system of the original recommender, the language of the original recommender system, the language we adapted to if there was an adaptation needed. Here, as you can see, it's from a core, so there is no adaptation needed. Then the editor we integrated, and how many line of codes was automatically generated for this integration. So if you can see here, there are 0 maps, because for these there is no mapping need. But then the other ones are from 5 to different 9 mappings, depending of if the tool supported attributes and operations, or if the tool only support operations alone. So these are images from this evaluation integration. So if you can see here too, this is a core tools. So these, as I mentioned before, automatically create this here in the menu that's called recommender, and then you select which type of recommendation you want, and then you can see this information here of all the recommendation items. And this is another example for UML3 editors, basically the same. You have somewhere in the menu a recommender with the options that you can automatically use in your modeling tool. So to answer the different, the 2 research questions, if we can reuse or adapt these existing recommender systems to different languages, the answer is yes. We reuse them for a core, UML, entity relationship, and EFML. And the only requirement for these was the mapping that can come from 0 to 9, depending of the particular case. And if we can integrate an existing recommender system, existing modeling tools, and the answer is also yes. So we integrate this in 6 different modeling tools that are based in Sirius and EMF. And as I mentioned before, all these integrations are with third-party modeling editors, and we did not need to access to the source code for these integrations. So as conclusions, we have proposed an approach to reuse and integrate recommended systems, and name it IronMan, based on a common recommendation API, mappings bridging the recommender system and the modeling notations, and rank aggregation algorithms. So IronMan is able to adapt and integrate recommended system within Eclipse modeling tools based on Sirius and 3 editors. So for future work, we want to integrate this aggregation that I mentioned before, that have board account and all this algorithm, till the moment don't provide any benefits. It's only a way to re-rank, or the benefits are really not much considerable. So we want to investigate more on using other type of aggregation algorithm that can actually improve the recall, the precision of these recommender systems. We want to extend our proposal using supervised rank aggregation methods, as we only work with unsupervised aggregation methods. We want to support integration with text annotations, such as xtext. And we want to explore other types of integration, meaning that currently you have to request every time you want a recommendation. So we want to also provide proactive recommendations during the modeling. Thank you. If you have any questions, this is the moment.
Thank you very much. Do we have questions? Could you go and use the mic in the middle so the live stream can pick it up? Okay.
Thank you for the great presentation. I have a question about the context that IronMan is sharing with the recommendation system. So with recommender system, it's very important to know the clients. Probably you and I have very different recommendations on Netflix. So when you're asking for a recommendation, for instance, for the professor class, what is the context that you share with the recommender system? Is it the entire modeling language in which you have the professor class, or is it just the professor class, or is it something else?
Actually, because here I'm only reusing already deployed, already designed recommender system, but the thing is, I didn't put everything because I didn't want to put too much technical thing. I just wanted to go light up. But here, sorry. Yes, here, I work with, if you check in the paper, there is like a meta model that serves as everything that is compliant to this idea. And here you see the context. So here you have already to explain which type of content you're expecting from your recommender, because every recommender, as you mentioned, is different. So we already support 3 different types of contexts. One is targets, which is the target, everything the target have, and everything of the same type of the target. None, if you don't request anything, or full, if you request everything that is happening within the modeling context. So that's the coverage we have in the model.
So is it in the configuration of the recommender system that the recommender system itself says, I want the full context, or I want nothing, or, okay.
Yes.
So it's part of the configuration of the recommender, and IronMan just adapts and gives the expected information.
Yes, there is still, this is the first paper we have in this tool. So it's kind of basic, covering everything that we consider. That's why we devise the dimensions. But right now, like this feature endpoint and the recommendation endpoint are pretty vital, that the one who wants to use it follow them and use the correct information and know what the correct expected. So there is a lot of assumptions that we won't know everyone what we are doing. So of course there is a lot of work to do there to be more ease on the user. But yeah, in the moment you have to specify and then also know that at the moment of the use of the tool.
Okay, thank you.
Very much.
Okay, any more questions? Okay, let's thank the speaker again in the usual way. Thank you very much.